Welcome back to the lectures on GPU architectures and programming. So, I believe in the last lecture we provided you with the basic OpenCL runtime overview, and we gave an example of a complete OpenCL program including the host code, primarily the host code I would say, like how to compile the code, how to build create the kernel, the different data buffers, the memory objects, and finally set up a context and create command queues and then execute the kernel by issuing suitable read kernel launch and write back and final read commands and all that. So, with this we will now move over to the next topic, which is again related to synchronization in OpenCL. So, if you remember in our coverage of CUDA programs also we had significant coverage on synchronization among threads, and it is a far more involved topic I would say when we are talking about OpenCL synchronization. So, here it primarily refers to mechanisms that will constrain the order of execution between two or more units of execution, like so just like if you remember in CUDA the synchronization primitive we were primarily using was sync thread, using which we could actually synchronize among threads inside a thread block, and if we wanted to achieve global level synchronization, that has to be managed through multiple launches of kernels through the host program, right. So, equivalently in OpenCL we have this concept of synchronization of work groups, which is essentially constraints on the order of execution for work items inside a single work group. So, this is the concept which is essentially equivalent to thread block synchronization in CUDA, and of course, we also have this idea of synchronization of commands, which gives constraints on the order of commands launched for execution, because if you remember in OpenCL at the end what you have is command queues which are being set up with this sequence of commands to be executed. So, you do not really launch commands directly, but rather you are just issuing commands, enqueuing them into the queue, and it is the runtime system's job to pick up commands from the queue in that order and execute them. So, you also have this scope of synchronizing the order of commands launched. So, let us first move into the idea of work group synchronization. So, this is essentially about synchronization between work items as we discussed inside a single work group. So, for this the OpenCL function we will be using is barrier, right, and for the barrier function takes as argument this CL memfence flags type variable, and from OpenCL 2.0 onwards we also have this command for work group barrier. So, this is similar command, but it provides you the notion that yes, this is about synchronization inside the work group, and for that you have this flag as well as another field called scope. For now we will just go with the flag. Now, what are the options for flags? First of all, again I will just repeat, the barrier command or the work group barrier command equivalently in OpenCL's current version, they would be synchronizing work items inside a work group. In the flag part you have two options, one is this CLK local memfence, and you also have this global memfence, right. The issue with this memfence is that what is the area of the memory you want to make visible to the work items who are synchronizing, right. So, whether it is the local memory or the global memory, upon that it depends what flag you are going to choose. All work items in a work group must execute the barrier before they are allowed to continue execution beyond the barrier, and it must be of course encountered by all work items of a work group executing by the kernel or none at all. Now, this is very important. First of all, let us understand that you have to have the primary semantics of barrier is that every work item inside a work group will reach the barrier, and once all of them reach it, only then any work item can go beyond the work group, right. The next important thing is you may be thinking, well, if I have placed the barrier inside an if else block, then maybe some of the work items will be facing the barrier and some of the work items will be bypassing the barrier. Well, that is not true. The semantics of barrier is that you have to write the code in such a way that either all the work items are supposed to execute the barrier, they have to encounter the barrier, or everybody will bypass them, because the barrier by its the runtime system by its definition of the barrier would wait for all the work items to be encountered. If it's partial, then it will be waiting continuously, whereas the other work items are not even facing it because of, let us say, an if-else based divergence, and that would create a deadlock, right? So it's up to the programmer to write the code in such a way to ensure this last property, right? Now, just to recall here about the flags. So I believe the barriers semantics is clear to you. It's a synchronization primitive, just like CUDA, but also like in CUDA, the synchronization primitive, the way you use it, you have to make sure that either all the program threads in the work group encounter it or none at all, so that you can avoid the deadlock issue, right? Now, regarding the flag, as I said, that if you set the flag as local memfence, then you make all the updates in the local memory visible to the threads in the work group, and similarly, if you set it as global memfence, then you are essentially setting making all the updates in the global memory visible to the work group. So that actually provides you an additional flexibility. Depends on what you are setting here. You are directing the runtime system that what you really want, what kind of behavior do you want with respect to the memory. So the barrier is controlling the way threads synchronize, and the memory fence and its setting is controlling the memory is being visible at what level to the synchronizing threads. Okay. Now, also I would like to add that in the newer version of workgroup barrier, there is an additional flag here called scope. If you are interested, if you want to go more into the more advanced concepts of OpenCL, well, you can go there. Get into that and figure out what is this idea of scope that comes with the flags for memfence, right? So now we proceed to some example on workgroup synchronization. So let's take this example of a simple kernel. So first, what you do is you execute the simple get global ID and get local ID calls, using which you are caching data from the global memory to the local memory. So I hope by now you are familiar with this get global ID and get global ID calls, get local ID calls in OpenCL. Essentially, they are helping you to figure out what is the global ordering of the threads and what is the local ordering of threads inside the work group. Using the local ordering of threads, you are figuring out in which position of a local buffer you will be writing a value, right? So once you have cached the data, you want all the threads to reach this barrier to wait at this barrier until all the threads are done with the previous job assigned to them. And after this barrier synchronization with respect to the local memory, updates here, you are going to the next part of the code where you perform some operation and save the output in the buffer. So here you have defined some operation that you calculate an address based on this get local ID get local ID, and then you do something over that value. So there is some functionality here, but we are just trying to show that how things are going on. So if you look into the figure, for this kernel, you have launched multiple work groups. We are trying to convey this fact that this position of the, so this is the time scale, I would say, in this y-axis, right? And you have all the work groups being dispatched, right? As you can see that the barrier is being, the synchronization is actually happening at different points of time across work groups, but inside every work group, all the threads have to hit the barrier, synchronize, and then move forward. So this is one synchronization primitive using barriers that you can do. Now there are several other primitives we will see. One of the important things is OpenCL events. So that brings us to this notion of event objects. So an event object is used to track the execution status of an OpenCL command. Like as you know, that in OpenCL every execution is like enqueuing a command in a command queue. Every command's execution will have a corresponding status, and this status is can be polled by an event, right. So, the OpenCL API calls and enqueue commands to OpenCL command queue and creates new event objects which are returned in the event argument. In case of an error, if there is an error in enqueuing the command in the command queue, then the event argument will not return an event object, but otherwise it should be successful in returning an event object. And the API can query the value of an event from the host. For example, you can track the progress of a command by inquiring to the runtime system about the status of the corresponding event, the value of the corresponding event. We will see some examples. For example, for every enqueued command, these are the following valid status values that the OpenCL runtime system will provide. For example, it can have a value CL queued. So, just to summarize, every OpenCL command will pass through these 4 statuses, and for this corresponding to this status you can define an event. So, that means for every event it can be attached to a command, and the event will have these possible values, that whether a command is queued, whether it is submitted, whether it is running, or whether it is complete. Now, the OpenCL API relates to the event object, and there are a few ways in which you can actually, these are the following functions using which you can use and manipulate events. For example, CL create user event is used to create a user level event object. The status of an event can be set by CL set user event status. It will set the execution status of a user event object. CL wait for event will wait on the host thread in the host side thread for commands identified by the event object in the event list to complete. So, I mean there may be events for which you are waiting and you want to implement that kind of a behavior, that can be done by CL wait for events. CL get event info. So, this is like a query function which will return information about some event object. Now, CL set event callback is related to registering of callback functions for specific command execution status. So, the usage of callback functions is they can execute asynchronously. So, suppose you want that for a specific command you want to figure out whether it has reached a corresponding status or not, some specific status, whether it is completed, whether it is pending or not, and you want that whenever that event happens that it has reached that specific status, then some thread, some specific callback function will be asynchronously launched in the host side as a separate thread. Now, this registered callback function will be called when the execution status of the command associated with the event changes to some specific execution equal to or past the status that is specified by command exec status. So, just to make it very simple, using this function CL set event callback, you can command the system that wait, I want some specific function called a callback function to be launched when the execution status of this command becomes something that I specify. So, when that equality is holding, that means the execution status of that command is equal to whatever I have specified, then this specific callback function will start working. Now, why is that normal function not a normal function, but I call it a callback function? Because it will execute, because the host does not wait for it. It will be called and it will start executing asynchronously in the host side. We will understand it at the end with some examples. So, here I am just trying to introduce the definitions and concepts. Now, the next important thing that why do we use this idea of events? We will figure out that they also help us to provide synchronization of commands. Now, they can be performed by in terms of distinct synchronization points. A synchronization point between a pair of commands assures that results of command A happen before command B is launched. You may always want that, well, I have enqueued commands in multiple command queues, but the execution of some command in some queue should depend or should only start when something else in some other command queue may have happened. right? You may want some such dependencies to be satisfied. How do you do that? Well, you have to synchronize between commands. So let's try and understand this is different from synchronization among threads, like we have done in CUDA and like we have seen as examples in OpenCL. But here it's a bit different concept. We are trying to synchronize among commands that have been enqueued in the command queue. The synchronization points occur between commands in host command queries, command queues, and between commands in device side command queues. So synchronization points will occur, again I will repeat, between commands in host command queues and between commands in device side command queues. We will see some examples between them. And all OpenCL functions that enqueue commands return an event that identify the status of the command, like we have discussed earlier, that every command every command which is being enqueued, for it an event is returned, and by polling that event or by querying that event, I can always figure out the status of execution of that command. The value of this event which is being associated with the command while enqueuing the command will be set to CL complete when the execution is done. Now this is very important. Like so, I will just summarize that all this idea of events which you have been defining. The primary reason is you are enqueuing a command. At that moment, it will return the event. That event's value will be one of this based on the execution status of the command, and when everything finishes, it will reach this CL complete status. Now this synchronization points that we have defined in OpenCL, they include the following. For example, completion of a command. A kernel instance is complete after all the workgroups in the kernel and all of its child kernels have completed, right? Because all the workgroups must complete. We need to understand that inside a kernel you may be launching child kernels, those also has to be completed. Now only when that is done, this is signaled to the host, parent kernel or other kernels within command queues. So for every kernel there may be a parent kernel or other kernels. So this is signaled by the corresponding event that was defined while enqueuing this kernel execution command, and this finishing of the task of execution of the kernel is signaled to the host or the parent kernel, and it is done by setting the value of the event associated with the kernel to CL complete. So just to summarize, you have launched a kernel, during that enqueuing operation of the kernel, you have got an event automatically associated to it, or you can actually specify which event to associate to it. That event status will be set to CL complete when all workgroups of the kernel, and also if there were any child kernel, whether all those workgroups of all those child kernels, everything is complete, only then the event associated with the enqueuing of the kernel will be set to CL complete. Now we also have this other function CL wait for events, and this waits on the host thread for commands identified by event objects in event list to CL complete. The event specified in the event list will primarily act as synchronization points. So I believe this should not be there. So just a minor correction. So when I have CL wait for events, this function will wait on the host. So when I have this function, the last one, CL wait for events, this is simply suppose you have made it to wait for a set of events. That would mean until and unless those event objects will reach this status CL complete individually, all those events, then only this function's job is done, otherwise it is still waiting there. So that's another synchronization primitive. So just to understand, using completion of a command would mean you are attaching, or you may possibly attach your event definition to a kernel launch. When that kernel launch and its child kernels have all completed, you get that event being attached, being automatically assigned the CL complete flag by the runtime system. The other option to synchronize would be that in your code you have a CL wait for events function, and you provide that function with a set of events to synchronize on, when the runtime system ensures that those set of events reach the status CL complete, then this function will release and let the execution move forward. Now, apart from this, we also have this notion of blocking commands. So, these are also synchronization points, because we have to understand that if a command blocks, that means until and unless that command's execution is finished, the program thread cannot go forward. So, command execution can be blocking or non-blocking. If it is a blocking function, then the OpenCL API functions that enqueue commands do not return until the command has completed, right. Some of the blocking commands are CL enqueue buffer, enqueue read buffer, enqueue write buffer, both of them, if they are called with the option blocking read and blocking write to be set to CL true. So, as you can see that when you are making these enqueue commands of read buffer and write buffer like defined earlier, they also had a field where you can set this flag of blocking read and blocking write respectively, and in those cases they are blocking commands. That means if you do not set it, then they will fire asynchronously. That means without this read buffer or write buffer finishing, the host program may move forward to the next command, right, because they will just keep on happening without blocking the actual flow of the execution. But if you set them to blocking read or blocking write, then until and unless these commands are complete, the host program's execution will not go forward. And then you have command queue barriers. They ensure that all previously enqueued commands to a command queue have finished execution before any following commands enqueued in the command queue can begin execution. So, you have the command queue ensures that commands start executing in that order, but if you put a barrier in between, it ensures that all the command queue functions which have started executing in their order, they should finish before anything after the barrier even starts executing. The OpenCL API functions for this are CL enqueue barrier with waitlist, CL enqueue marker with waitlist. So, these are essentially you are enqueuing a barrier in the command queue. And of course, you can put the barrier with a waitlist, that the barrier first waits for the events in the waitlist, and then the barrier is active, and then all the commands previous to the barrier are forced to finish before further commands can be launched. You also have synchronization points defined by CL flush. So, if you have CL flush, then all previously queued OpenCL commands in a specific command queue are issued to the device associated with the command queue, and CL flush will guarantee that all these commands in that command queue will eventually be submitted to the appropriate device, and of course, there is no guarantee that they will complete after CL flush returns. So, it guarantees that all the commands in the queues will be submitted to the appropriate device starting from so you have enqueued them and you have submitted to, CL flush is ensuring that all of them get submitted to the device for execution, and then you have CL finish. So, for CL finish, whatever commands have been queued, they are issued to the associated device, and the function blocks until all these queued functions have completed. So, unlike CL flush, which is providing you a guarantee that whatever commands have been enqueued earlier, they are all submitted to the device from the command queue, CL finish, if it is executed and it returns successful, it is guaranteeing that whatever commands were enqueued and all of them have completed. So, this function blocks until all previously queued commands have been completed. It does not return until all the previously queued commands in the command queue have been processed and completed, and so I hope this is the difference that you can understand between flush and finish. And then for the purpose of synchronization, as we discussed, that you have command queue barriers and you have wait on an event primitive, and command queue barrier ensures that all previously queued commands have finished execution and they have updated whatever memory objects or memory objects for commands which will begin execution afterwards. So, this is the primary reason why you will like to have barriers, like the command queue ensures that you start issuing commands in that order, and if you put the barrier, you can actually ensure that though they finish all the commands that have been enqueued, they actually finish, and there are before going forward, and this can be used for important reasons. For example, as has been specified here, that you suppose you need some memory objects to be set up before further command queue execution goes forward, and you want some memory objects to be updated and ready by some kernels to have executed earlier, and only then you will be executing the next kernel. This kind of execution behavior you can ensure by using the command queue barriers. Now, the important thing is, inside a command queue, if you put a barrier, it will help you to synchronize between commands inside a single command queue and not across multiple command queues. Now, the other thing is waiting on events. All OpenCL API functions that enqueue commands, they return an event that identifies status of command. Like we have discussed earlier, events are returned by the enqueuing command operations only, and the events can have values starting from waiting, submitted, and all that to up to CL complete when the event finishes execution. And finally, you have this CL finish synchronization primitive, which blocks until all previously enqueued commands in the command queue have completed. Like we have already discussed CL finish and the difference between CL finish and CL flush. So, overall, these are the different primitives that we will be using. Now, the next topic would be out of order execution of kernels and memory objects. So far, we have assumed that yes, you have a OpenCL command queue, you have enqueued them, and they can just go and execute in order, but that is not going to hold true in general. Maybe we will end the current lecture here and resume from this point in the next lecture. Thank you.